Hello and welcome. Today we are going to discuss about loop antennas followed by slot antenna. Now in the last lecture we have talked about dipole antenna and monopole antenna. So let us just look into this here. So suppose if this is a dipole antenna which is carrying a current, we are feeding in the center here. Now for this particular case we saw that H field is like this here and E field is in this particular fashion, which is making a figure of 8 like this here. Okay. Now a loop antenna is nothing but a complementary of this. In a sense, if we take a small loop, then small loop will be, let us say, something like this here. Okay. We can actually look into small loop is like this. Now this small loop, if we assume that the current is uniform over here, so this can be thought about that if there is a magnetic dipole like this, then a magnetic dipole, see for example, if it is electric dipole, we will have a magnetic field. If it is now a magnetic dipole, then this will be electric field or a current is flowing like that. So in fact a small dipole antenna is nothing but we can correlate that with a magnetic dipole antenna. So whatever the derivations, whatever the calculations we did for the dipole antenna, they are valid for the loop antenna, in a sense that E field will become H field and H field will become E field. Open circuit over here will be closed circuit over here. So let us see about loop antenna today. So today, as I mentioned, we will talk about loop and slot antennas. So we will first cover loop antenna, then in the next one we will talk about slot antenna. So we will actually think about a very small loop. Let us say this small loop is put around the origin. So this is the origin here, x axis, y axis, z axis, and as before we are going to measure phi angle from x axis, theta is measured from the z axis, and these are the components which are the field component at any far away distance r. Now we can actually start with the, let us say, a circular loop or a square loop. In the beginning we will just look at the small circular or square loop. Small means whose circumference is much less than wavelength. Now in this particular case, as I mentioned, if we assume that there is a uniform current, then this can be approximated as a magnetic dipole over here, and along with that there will be electric current. So all we need to do it is we use the same concept of the dipole antenna, except that we change E field to H field and H field to E field. So for this particular case, when the loop dimensions are small, now by the way, this can be a single turn loop, it can be multiple turn loop, the loop can be wound in the air itself, or it can be wrapped around a dielectric which can be solid or hollow, or it can be even a ferrite material also. So we will see one by one what are the different scenarios. So let us first look at the radiation pattern of the loop antenna. Here we have taken a diameter which is lambda by 10. So circumference will be equal to pi times d. So C lambda is nothing but C divided by lambda. So that will be 0.314, which is nothing but pi divided by 10, that is the value here. And here the loop is placed in this particular fashion over here. Okay. So if the loop is placed over here, and we are saying that this particular loop will be equivalent to a magnetic dipole, which will be something like this here. So for a dipole we know that there will be no radiation in this direction. So here also for the same, in the same way for loop antenna there is no radiation over here. So please remember, loop is placed like this here, and then the pattern in this particular plane is nothing but making a figure of 8 shape, and if you look at the pattern in this plane here, that will be circular, just like a dipole antenna. But now this is actually a, instead of electric field earlier, now this is a magnetic field, and the field which will be uniform along this direction now will be electric field. So now we will look into the different patterns. So let us say for diameter equal to lambda, C lambda will be this. So now this pattern changes, it is not maxima in this particular direction. Again this is somewhat similar to a dipole antenna. For larger length dipole antenna, radiation is not maximum here, but radiation is maximum in this direction. Now these are Now further larger ones, instead of lambda it is 3 lambda by 2, 5 lambda. But I just want to tell you that this is not really a real scenario. In a real scenario, current will never be uniform along the loop. Okay. So that is why theoretically it is okay, we can assume anything. Practically this is not going to be feasible. So in general, very rarely these kind of antennas are used. The most popular antennas are only this one here, where loop antennas are taken smaller in diameter or circumference, and for that we know that this is the radiation pattern. So for this, then for single turn loop we can actually find out what is the radiation resistance in a very similar way. For dipole antenna, what we had done, we found E, then from E we also knew H field, and then power was calculated by integrating E and H, and then power was equated to half I square RR. So the same way we have to do the same thing. So we get a radiation resistance which is given by this formula here. Now please recall, for a small dipole antenna, radiation resistance was 20 pi square L by lambda square. Here the difference is, it is to the power 4, but this is for small loop antenna, where C is circumference. Circumference is nothing but 2 pi A, which is also equal to pi D. Now most of the time we do not use a single loop antenna, we use multiple turn loop antenna. This will be obvious when we take this design example here. So if we take n turns, for n turn RR increases by a factor of n square. So radiation resistance can be increased significantly by increasing number of turns, then RR increases by n square. Now for large loop antenna, the value is given by this particular expression. I want to tell again, most of the time we do not use large loop antenna, but nevertheless let us just see here. So this expression is valid for C by lambda much less than 1, this expression is valid for C by lambda much greater than 1. Let us see what really happens if C by lambda is 1. If C by lambda is 1, this expression will give me roughly 200, because pi square is approximately 10, and this one here for C by lambda equal to 1 will give roughly 600. So we know that for C by lambda equal to 1, neither of these two formulas are correct. It will be between say 200 to 600 ohm. So let us just take an example. Here the example we have taken is C by lambda is 0.1. So if we now substitute this value over here, what we get is 0.02 ohm. Now you know that this is a very, very small impedance. If we try to feed this 50 ohm coaxial feed, it will result into a large mismatches, and most of the power will reflected back, very little power will be transmitted. But here now if we take n equal to 50, so n equal to 50, this has to be multiplied by 50 and 50. So 50 multiplied by 0.02 will be 1, another 50 will give us 50 ohm. So you can actually see that if I take a C by lambda equal to 0.1, use 50 turn, we can get a good matching with the 50 ohm coaxial feed. So that is a very simple way to design an antenna. Now these are the relations for radiation resistance versus loop circumference. So actual value calculated is something like this here, which is varying sinusoidally but increasing along this line here. So this particular variation has been approximated by two equations. One is this equation that is valid for very small loop antenna, and one can see that for the real value here this approximate formula is matching fairly well, but for larger loop antenna this is the expression given by this 60 pi square C by lambda. And again I want to repeat that most of the time you do not use a large loop antenna, generally use a small loop antenna. So this expression is relatively okay, and this is what you need to use majority of the time. So now many a times this loop antenna is actually put on a ferrite core, and I will tell you the reason also where it is done also. And a practical example is AM radio receiver generally uses loop antenna which is wrapped around a ferrite core. So if it is wrapped around a ferrite core, then the actual radiation resistance will increase by a factor of mu square, because, and here it is used as a effective mu, because some air might come into picture in between when you put a loop antenna around a ferrite core. Okay. So this is the expression to be used, and let's just look at one example. So let's say we have a n turn circular loop antenna whose diameter is say 2 centimeter, and the wire diameter is thin, which is a 0.2 mm. Now this is put on a ferrite core whose effective permeability is 10, and what we need to know is how many turns are required to obtain 50 ohm impedance at 3 megahertz. Now at 3 megahertz, what is the wavelength? Wavelength is going to be 100 meter. So that is a wavelength lambda. 100 meter we have converted into centimeter, so that becomes 10,000 centimeter. Desired R input is 50 ohm, which comes over here. Mu is 10, so 10 square, 20 pi square comes here, and C is nothing but pi times D, and D is equal to 2 centimeter. And if we use this here, one can now see, calculate this and find out the square root of n square, which comes to this. You can see that it requires about 127,485 turns. Now you just imagine, if it was not a ferrite core, if it was air, then this number will change by a factor of 10. So if it was wrapped around just air, then this number would actually increase by 10 times. Okay. So that is the advantage of using a ferrite core, that you can reduce the number of turns. So here is the expression for the directivity. So here we have a loop circumference normalized with respect to wavelength, and this is the directivity in dB. Now for a very small loop, which is actually here, so very small loop, you can see that the directivity is slightly less than 2 dB, which is somewhat similar to for a dipole antenna, which is a small length dipole antenna. We saw that the directivity is of the order of 1.74 dB, so it is very similar to that. Now one can see that the directivity increases with the loop wavelength. However, if we just look at it corresponding to wavelength of 10 here, which is the normalized things, loop circumference, so 10 times wavelength, if you corresponding here, if we see here, we are only getting about 8 dB or so. However, if we use different type of antennas, or if we use arrays of antennas, we can get much larger directivity. Hence this one I strongly recommend never ever to use it. So now in the last lecture, if you recall, I did mention, we talked about a folded dipole antenna, and I did tell you that folded dipole antenna can also be thought of as a rectangular loop antenna. So just have a quick thing here. Suppose if it was just a dipole antenna, for a dipole antenna fed with plus minus 1, so this is the dipole antenna. We have done the simulation for these dimension. So where the length of each segment of dipole, which is 50 mm here, 50 mm here, the width is actually taken as 2 mm, and the air gap is taken 2 mm here. So just for this particular dipole antenna, the impedance is about 70 ohm, and resonance frequency is close to 1.5 gigahertz, and that can be very quickly looked into it. So if I just say approximately, this is 50 and 50, so that will be 100 mm, that is approximately equal to 10 centimeter, corresponding to 10 centimeter. Wavelength will be, that is a wavelength, if we take 10 centimeter as lambda by 2, then wavelength will be equal to 20 centimeter, which corresponds to frequency of 1.5 gigahertz. So you can see that it is very close to that. Now for a folded dipole antenna, we had seen that for a folded dipole antenna, impedance is 4 times Z input of dipole antenna. Now by the way, these are all simulated results, we have simulated using i3D software. Now when we looked into this folded dipole antenna, that particular equation doesn't say anything about what is the length of this connecting strip here. So what we have done here, we have used variable as a connecting strip length here. So we have taken this over here as 3, 6, 10, 20, and the width of the connecting strip has been taken as 1 mm. So, now if we just notice here, so as we increase this width here, so the resonance frequency keeps on decreasing, okay, and impedance is roughly 4 times. You can see that 70.3 multiplied by 4 will be about 281 ohm. So, we are getting about 286, which is close, but as this strip length increases, it is this expression or the impedance is increasing slightly. Now, this phenomena cannot be explained only by this over here. Also, if we notice, as we keep on increasing the strip length 3, 6, 10, what is happening? We can see that the resonance frequency is decreasing. Again, that phenomena cannot be explained by just this particular expression here. However, this phenomena can be very easily explained if we assume that this whole thing is now acting as a loop antenna. Then when this connecting strip length is increasing, what will happen? The total loop circumference will increase, and if the circumference increases, and we can actually just notice here that circumference approximately equal to lambda. So, if we just add up all the dimension and calculate the resonance frequency, you will see that with increase in the strip length here, the total length will increase. So, resonance frequency should decrease. So, a folded dipole antenna can be very easily explained by rectangular loop antenna. And also please recall, I did mention when circumference is equal to lambda, the limit can be between 20 pi square, which is 200, to maximum 60 pi square, which is 600. So, between 200 and 600 ohm, this is what we are getting it for the lambda equal to C. So, here are some of the plots here. So, what we have done, we have taken a little larger loop here. So, connecting strip is taken as a 20 mm long over here, and this whole thing is total is 100, 2 mm, this is 50 and 50 with a gap of 2. So, for this we can see actually the input impedance plot, and I want to show that we started with the very low frequency simulation. So, at low frequency one can see all these things are inductive. Okay. Now, recall for a dipole antenna, it was all capacitive. Now, this is a reverse of that. So, this is now all inductive here, and you also know that for a closed this thing, it acts like an inductor, or a multi-turn loop also will act as an inductor, and that is why impedance is inductive. And one can actually see that there is a resonance first coming over here. So, this is the fundamental resonance, okay, which we had seen in the previous case, for which impedance is close to 300 ohm. We can just check that. So, corresponding to this here, impedance was roughly 300 ohm. So, in the Smith chart, we know that this is about 50 ohm here, that is close to 300 ohm, and then this one here is actually corresponding to the second order mode, and the second order mode can be determined whenever circumference is equal to n lambda. So, for n equal to 1, it will be the fundamental mode, and then n equal to 2, 3. So, this result is actually for the second order mode, and one can see the deflection coefficient plot. So, this is the value corresponding to the fundamental mode, and this is the value corresponding to the second order mode. This is the value corresponding to the third order mode, and one can actually see that from here this is approximately double of that value. So, we see that it is not matched with the 50 ohm, because input impedance is close to 300 ohm, it will not be matched with 50 ohm. Now, let us see what is the radiation pattern. So, even the case which we are looking at, so radiation pattern at 1.32 gigahertz, at which this whole circumference was equal to lambda, even for that the radiation pattern is very similar to that of a dipole antenna, except that E field has become H field has become E field. So, we can see that the maximum radiation is not in this direction, but it is in this direction, which is perpendicular to the loop axis, and perpendicular to the loop there is a no radiation, which is given by dark blue. So, we know that dark blue is the least radiation, and green, then yellow, orange, red shows maximum radiation. Now, I have shown the radiation pattern at the second order mode. You can see that the radiation is maximum in this direction, in that direction, as well as in this direction here. So, majority of the time this is not really used. So, we generally use the fundamental mode only, or in fact majority of the time we use small loop antenna, which could be a multi-turn loop antenna. And you can see that here gain is actually close to 0 dB. It is not the directivity. Directivity may be close to 1.52 dB. Gain is less because matching is not very good at this particular point here. One can see that at this point, because of the good matching, gain is also higher. Okay, you can see that the higher value of the gain, which is approximately 5 dB. So, let us just look at one of the typical application of a loop antenna. So, we did look at one of the application where the loop antenna was wound around the ferrite core there, but now let us just look at another application. In fact, loop antennas are finding lot of application these days in RFID tag. What is RFID tag? Radio frequency identification. So, let us see what we have here. So, one can actually see that there is a one, this is the chip which is put over here, and that is the padding where the connection is done. So, one turn of the loop, let us just follow here. So, the loop is going over here, is going around. This is printed on a flexible PCB, or you can call it a substrate, and it is actually going from here going all the way. So, the loop antennas, it almost looks like a spiral antenna also, but it is still a loop antenna. And then the last turn over here, you can see that a plated through hole is made over here, and through the other side, then from the back side of the substrate, it is actually connected over here. So, one can see that this is a multi-turn loop antenna which is actually going to the RFID chip. So, this is the one of the application. In fact, majority of the RFID tags are either using something like this here, or in the last lecture I even showed an application where RFID had used a dipole antenna. So, here the application of loop antenna is there. In fact, some of these things, for example, this particular RFID tag which I showed you, that application is for 13.56 megahertz. Now, at 13.56 megahertz, if one tries to use a dipole antenna, the length will be very, very long. However, a multi-turn loop antenna can be used, which will actually still be in a very small area. So, the area is important, because many of these RFID tag, their size is actually almost fit onto a visiting card of about this size here. So, we need a compact antenna which should fit in that particular size. Many a times I just also want to tell that capacitance is also put in parallel, so that we can create a resonance also. In fact, I would like to emphasize for AM radio. Now, AM radio frequency ranges from 530 to 1620 kilohertz. So, if I take a in between frequency which is 1 megahertz. Now, at 1 megahertz wavelength is about 300 meter. Now, you can't have an antenna of 300 meter for a receiver. Now, just to mention, for AM transmitter, they generally use lambda by 4 monopole antenna. Now, lambda by 4 of 300 meter will be 75 meter. So, 75 meter is almost, if I take a building height as 10 feet, which is equal to 3 meter. So, 75 meter tall will be about 25-story building. Now, we also need a radio receiver which is going to be this small. So, for radio receiver working at, let us say, around 1 megahertz. So, what we need? We use actually a loop antenna, and it is actually wrapped around a ferrite core, and then the two ends of the loop antenna are actually terminated with the variable capacitor, and that variable capacitor. So, when you change or tune the radio station, all you do it is you actually change the value of the capacitance. So, resonance frequency is given by omega 0 is equal to 1 by square root LC. So, this loop antenna does two things. One is it is acting as an antenna, another thing is it is acting as an inductor, and you put a capacitor in parallel to that and change the capacitor value, and that is how you tune the radio station. So, loop antenna are used in some of these applications, and RFID has been used, I mean they are using loop antenna in so many different applications. In fact, many a times these loop antenna are also used for sensing the magnetic field at a given place. So it is a good antenna to be used, but most of the time it is the small loop antenna which is used, not really the large antenna with respect to the wavelength. So just to summarize, we talked about a loop antenna, and we recommend strongly only to use small loop antenna. It can be multi-turn so that you can do the impedance matching properly, and typically total circumference length should be approximately lambda, so that the resonance condition is obtained. And then we also saw that if you use number of turns, then R increases by n square. Of course, I want to again emphasize, it is not just radiation resistance, it also has an associated inductance. So at lower frequency inductance is there, and that is why sometimes we put capacitance to tune it out, or you can use a larger number of loop turns, and then we saw that you can get just a real number also, and which can be fed directly with the coaxial feed to do the matching. And then we looked at some of the application. So in the next lecture we will talk about slot antenna. Again, just to tell you, slot antenna is nothing but a complement of a dipole antenna. So whatever is good for the dipole antenna, it is again good for the slot antenna, except for the difference. In the case of dipole antenna, whatever is E field, it will become H field, and H field will become E field. So in the next lecture we will see how to design a slot antenna. Thank you.